The binomial theorem states that if you have x plus y to the n power, you can actually rewrite it as the sum from k is equal to 0 to n of n choose k times x to the n minus k times y to the k power. Now, if you're trying to do something like x plus y to the second power, that's pretty light, right? You just FOIL everything out. But what if you want to do something like x plus y to the sixth power? I don't want to do all that work. So what I'm going to do is, let's see if I can expand this out using this binomial theorem. All right. So what's going to happen is, imagine if k is equal to 0. So remember that for summation, you start at k is equal to 0, and then you go until its end. So actually, let me just rewrite this down. So we are starting from k is equal to 0, and we're going all the way up into n, where n basically represents, right, the power that we're raising our thing to, right? So in this case, we're going up from k is equal to 0 to 6, right? Because 6 is our power. Then this is going to be n choose k. So in this case, 6 choose k. And then this is going to be multiplied by x to the n minus k. So x to the 6 minus k times y to the k power. All right, now that we have all of this written out, let's start expanding this. So what we're going to do now is imagine if k is equal to 0. So we're just going to slowly go up from integers between 0 to 6. So when k is equal to 0, we are going to have 6 choose 0 times x to the 6 minus 0, which is just x to the 6, times y to the 0th power, right? Because k is equal to 0, right? So everywhere we see a k, we just substitute 0 in. Then we're going to go to 1, right? Because remember, summation is from, in this case, 0 to 6. So what we're essentially doing is we're plugging in values between 1 to 6, right? These integers between 1 to 6, right? And we're going to go through all of them one at a time. So when k is equal to 1, we're going to have 6 choose 1 of x to the 6 minus 1 times y to the first power. And x to the 6 minus 1 is just 5, y to the first power is just y. And it's going to be plus 6 choose 2 times x to the 4th power times y to the 2nd power. And you kind of see the pattern here, right? You're just going to increase basically the bottom of this choose thingy, and you're going to decrease this power and increase this power by 1 every time. So it's going to be 6 choose 3 times x to the 3rd power times y to the 3rd power plus 6 choose 4, 6 choose 4 times x to the 2nd power, y to the 4th power plus 6 choose 5, x to the, sorry. All right, and this is going to be plus 6 choose 5 times x, y to the 5th power, x to the 1st power, times y to the 5th power, and plus 6 choose 6, and it's just going to be x to the 0th power, y to the 6th power. Right, notice how all of our exponents add up to be equal to the power that we were raising it to. And we're essentially just going to do that for every single one of it. And if you don't know how to do the choose thingy, well, I mean, you could just use your calculator. If you have a TI-84 calculator, go to math, go to probability, and you go on this 3 right over here, n choose r. So in this case, if I'm trying to find out what 6 choose 0 is, well, this is just going to be 6 choose 0, and that's going to be equal to 1. What the 6 choose 0 is, and by the way, if you guys don't know what n choose k is, this is just going to be equal to n factorial divided by k factorial times n minus k factorial. Right. This is essentially, if we're trying to solve 6 choose 0, we're essentially saying that if we have 6 things, so let's say if I have 6 things, how many ways are there for me to choose 0 objects out of the 6? And there's only one way I can do that, which is just choosing nothing, right? This is why 6 choose 0 is 1. If I were to, let's say, look at 6 choose 1, right? So if I put 6 choose 1 in my calculator, I'm going to get 6. Right? And that makes sense because if I have 6 objects, 1, 2, 3, 4, 5, 6, how many ways are there for me to choose one object kind of out of these 6 objects? I can choose either this one, this one, this one, this one, this one, or this one, right? So out of these 6 things, I'm able to choose one object, kind of like there's 6 different ways for me to choose one object out of these 6 balls, right? So yeah, that's why 6 choose 1 is equal to 6. And you can also do this using this formula, right? So it's going to be n factorial. So in this case, we have 6 total objects divided by k factorial. K factorial is going to be basically the number on the bottom. So 1 factorial times n minus k factorial, or 6 minus 1 factorial. 6 factorial is just going to be equal to 6 times 5 times 4 times 3 times 2 times 1, right? So 6 factorial, we can rewrite this as 6 times 5 factorial, right? And on the bottom, the 1 factorial is just equal to 1, so we could just ignore that. And we have 6 minus 1 factorial, aka 5 factorial. The 5 factorials cancel out, and we get 6 once again. All right. Let's do another kind of example. So let's say if we're trying to expand, let's say 2x plus 3 to the 5th power. All right. Now, I can do this using the binomial theorem, but the problem is that the 6 choose whatever, that's a little too annoying for me. So what I'm actually going to do is I'm going to use something called Pascal's triangle. Basically, the ones are to the side, right? So you have ones to the side, and you're just going to add up the numbers. So hopefully I don't have to explain. Hopefully this visual is good enough. But you're basically just adding up the numbers sort of sideways, right? So all of these numbers, 3 plus 3 makes 6. This makes 4. I add another 1 to the side. This makes 5. This makes 10. This makes 10. This makes 5. And then if I add more 1s to the side, this makes 6. This makes 15. This makes 20. This makes 15. And this makes 6. Pascal's triangle is great because, look, let's say if we have x plus 1, or actually x plus y to the 1st power. Actually, let me do this. Let's say if we have x plus y to the 0th power, that's equal to 1. Let's say if I have x plus y to the 1st power, that's going to be equal to 1x plus 1y, right? Because it's the 1st power. Let's say if I have x plus y to the 2nd power, that's going to be equal to x squared plus 2xy plus y squared. Notice how the coefficients match up with what the Pascal's triangle is saying. X plus y to the 0th power, we get 1. X plus y to the 1st power, we get 2 1s. X plus y to the 2nd power, we get 1, 2, 1. All right. So for the 0th power, we're going to use this first row, the first thing, and then this is, if we're trying to find x plus y to the 1st power, we use this row. This row we use the 2nd power. This is the 3rd power, 4th power, 5th power, 6th power. So basically all of these tell us sort of the values for our n choose k, right? If we're trying to find out what 6 choose 0 is equal to, just look at the Pascal triangle, notice how it's equal to 1. If we're trying to find out what 6 choose 1 is equal to, well, look at the thing, and we get 6, right? And those are the things that we mentioned before that were correct. So yeah, you can also use the Pascal's triangle thing to help you. I'm just going to use this row right over here. This is going to be for my problem here, 2x plus 3 to the 5th power. So how am I going to expand this? Well, normally, remember, we would have to do 5 choose 0, and then 2x to the 5th power times 3 to the 0th power, right? And then we would do 2x to the, we would do 5 choose 1 times 2x to the, this has to be in parentheses, but 2x to the 4th power times 3 to the 1st power, right? And it would be pretty annoying. But with Pascal's triangle, well, I can, instead of writing all the choose thingies, I can just be like, okay, 2x plus 3 to the 5th power, that's going to be equal to 1 times 2x to the 5th power times 3 to the 0th power plus, and then take a look at the next term. That's a 5, right? So we're going to do 5 times 2x to the 4th power plus 3 to the 1st power, times 3 to the 1st power. And then this is going to be plus, and we take a look at the next term, 10. So we're going to have 10 times 2x to the 3rd power times 3 to the 2nd power. And it's going to be plus, and we take a look at the next term, which is another 10, right? 10 times 2x to the 2nd times 3 to the 3rd power. And it's going to be plus. We take a look at the next one, that's 5. 5 times 2x to the 1st power times 3 to the 4th power. And finally plus, and another 1. So 1 times 2x to the 0th power plus, times 3 to the 5th power. All right, and this is going to be extension. The rest of the thing, right, to find all that, hopefully you should be able to do with a calculator. But yeah, that's pretty much it. That's pretty much all for this. Also, it's pretty cool that, so let's actually make sense of the binomial theorem, and to help you understand this, so that it's not just memorization, right? You actually get the concept. So x plus y to the 3rd power, you're going to have x to the 3rd power plus 3x squared y plus 3y squared x, or actually 3xy squared, same thing, and then plus y to the 3rd power. Now, x plus y to the third power is the same thing as x plus y times x plus y times x plus y. All right. Now, notice how, right, imagine if you have 3 slots. So imagine, right, because this is raised to the third power, imagine if all of these represented a slot, okay? So all of these represented a slot. Now, right, we can have different sort of possibilities to have, right? We can either get out an x to the third power, right? If all these slots are x's, we can get an x to the third power, right? If 2 of these slots are x's and one of this slot is y, we get x squared y, right? If 2 of these slots are y's and one of these slots are x's, well, we're going to get y squared x, or xy squared, right? And then if all of these slots are y, we're going to get y to the third power, right? But what the hell determines the coefficients in front of these terms, right? How do we get 3x squared y and then 3xy squared without doing all the foiling, right? With the foiling, I can clearly see that, you know, everything kind of works out, but how do I do this in this case? Well, imagine if we wanted to get an x squared y term. So imagine if I'm looking at actually, let's start from the beginning. Imagine if I want an x to the third power term. All right. Now, right over here, I have 3 options in total, right? I have 3 sort of slots in total. From 3 slots, I'm going to choose 3 of them to be x's. So how many ways are there for me to choose 3 objects, right? So if I have 3 objects, right? Essentially, how many ways are there for me to sort of rearrange this if we don't really care about the order of the objects? And the answer is that there's only one way for me to do this, right? There's only going to be one way for me to do this. Because guess what? If I have, let's just say these are 3 humans, right? And we wanted them to line up. Remember that combinations, we don't care about the order that they line up in. So it doesn't matter if we pick Bob, then Jane, then Marley, whatever, right? It's going to be the same people, right? If we have 3 people in total, we're choosing all 3 of them to line up, but we don't care about the order that they line up in. Well, there's only going to be one way for them to be arranged, right? So yeah, that's why we have a 1 here. Now, let's say that if I wanted to get this x squared y term. Now, the thing about this x squared y term is that there are multiple ways for me to get an x squared y, right? I can have 2 x's in the first part and then 1 y in the last part. Or I can have 2 x's like this and then 1 y in the middle. Or I can have 1 y here and then 2 x's here, right? So we have basically essentially 3 things, 3 slots, and we're choosing 2 of the slots to become x's. Because if 2 of the slots are x's and we want to get an x squared y term, we know the last slot has to be y, right? So essentially what we're doing is we're finding the total amount of possibilities, or sort of the total sort of combinations where we get an x squared y term, right? We're choosing 2 of them to be x's, and we're seeing the different sort of possibilities that, you know, or the different amount of x squared y terms that can be made if 2 of these slots are x's. So how many ways are there for me to rearrange these 2 x's so I get an x squared y term, right? And it turns out that I can place an x, 2 x's here, and I get a y. That's one possibility. I can place 2 x's here and get a y. That's another possibility. I can place 2 x's here and get a y. So that's 3 ways I can do this. All right, so that's why kind of sort of the binomial theorem works. What you're essentially doing is you're essentially choosing a couple of them to be like the x's, right? And then essentially choosing a couple of them to be x's, and you're seeing how many ways are there for me to rearrange the x's so that I can get this desired value, right? Because when you're foiling it, there's many ways to sort of multiply it, right? There's all these possibilities for these multiplications. So yeah, you're just going to be multiplying everything. So how many ways are there to do that for every term?